Welcome back to the deep dive. Today, we're tackling a paradox that has been effectively haunting the world of artificial intelligence for the last few years.
Yeah, the classic bigger is better dogma.
Right. You know that we've been told that if you want a smarter AI, you need a bigger AI. More parameters, more data, massive data centers, and an energy bill that looks like the GDP of a small country.
Exactly. For a long time, the only way to improve performance was to scale up. But that scaling has, well, it's hit a wall,
Yeah.
both in terms of hardware limitations and, frankly, the environmental impact. It's just not sustainable.
No, it's not. But what if I told you that the secret to the next generation of AI isn't making it bigger, but making it radically simpler?
Radically simpler. I like that.
Yeah, so today we're doing a deep dive into the foundations of generative AI, the state of the art. Specifically, a paper that, frankly, sounds kind of impossible.
It really does.
It's titled The Era of 1-Bit LLMs. All large language models are in 1.58 bits.
Which is such a provocative title.
Yeah.
And this comes from a collaboration between researchers at Microsoft Research and the University Chinese Academy of Sciences. And they are proposing something that effectively defies those previous laws of scaling we just talked about.
So the mission for this deep dive is to figure out how you can shrink let's call it the brain of an AI without making it stupid. Because that's the trade-off, right?
Usually.
Like if you compress a file, you lose quality. But these researchers are claiming they can use a system based on just 3 values, just -1, 0, and 1.
Yep.
And somehow match the performance of those massive power-hungry models we use today.
And not just match them. That's the crazy part. They run dramatically faster and cheaper. It is a potential game changer for how we think about computing intelligence altogether.
Okay, so let's unpack this, because before we get into the solution, I think we really have to understand the status quo. Why are current AI models so heavy? I always hear this term floating points.
Right.
What does that actually mean in this context?
Yeah. So think about traditional large language models, like LLaMA, for example. They're built on what we call 16-bit floating point values.
Okay.
You'll often see it written as FP16.
Okay, analogy time. Imagine I'm trying to do basic math, but every single number I use has to be written out to 16 decimal places.
Yeah.
So instead of just saying, like, 5 times 2, I have to calculate 5.000000000000000 1 times 2.000, and so on.
That is actually a really accurate way to visualize it. And the computer has to handle that exact level of precision for billions of parameters.
Billions.
Billions. And the heavy lifting there comes from 2 places. First, matrix multiplication.
Right.
The bulk of what a large language model actually does under the hood is multiply these complex, high-precision numbers together.
Which obviously takes a ton of computing power.
Immense power. And then the second bottleneck is memory. You have to move these really heavy parameters from the DRAM, which is the main memory, to the on-chip memory, just to do the math. Transferring that much data back and forth is incredibly slow and expensive.
It's like the commute is harder than the actual job.
Exactly.
You're spending more energy just getting the numbers to the processor than you actually crunching them.
Precisely. We call that the memory wall, and when you're dealing with high-precision floating points, that wall is very, very tall.
So we've got these heavy numbers that are hard to move and hard to multiply.
Yeah.
Now, I know there have been attempts to fix this before.
Yeah.
We hear the word quantization thrown around a lot. Isn't that basically just squishing the model down?
Yes. Post-training quantization is the standard industry trick right now.
Okay.
You take a big 16-bit model that has already been trained, and you try to compress it down to, say, 4 bits.
Right.
It saves space, sure, but the paper we're looking at argues that this is fundamentally suboptimal.
Suboptimal how? Like, what's the catch?
Well, you're essentially taking a high-resolution photo and JPEGing it over and over until it gets artifacted. You lose accuracy. The model just wasn't designed to be small. You're just forcing it into a smaller box after the fact.
Got it. So it's just a compression trick, not a new architecture. You're kind of trimming the fat, but you aren't changing the bone structure.
Exactly. The researchers argue we don't need a better compression algorithm. We need a model that is born efficient. We need to train it from scratch to be small.
Which brings us to the star of the show, BitNet b1.58.
Yes.
First of all, we have to address this name, 1.58 bits. How can you have 1.58 of a bit? Is it a bit and a half?
I know, it sounds like a typo, doesn't it?
It really does.
But it's just math. In a standard binary system, you have 1 bit representing 2 possible states, 0 or 1.
Right.
But this model uses a ternary system. It has 3 potential states for every single parameter. -1, 0, and 1.
Okay, so 3 states.
Mathematically, the information capacity of a system with 3 states is the base 2 logarithm of 3, which is approximately 1.58.
Okay, so 1.58 bits is really just the incredibly nerdy way of saying 3 options.
Precisely. It's an information theory term. But in practice, it just means every weight in the network is one of those 3 integers.
Now, here's where it gets really interesting to me, because there was a previous version of this, right, called just BitNet.
Yes, the original BitNet.
And that was purely 1 bit, just -1 and 1. But this new paper adds 0 into the mix. Why is 0 such a big deal? It seems like a pretty small addition.
Oh, the power of 0 is massive here. In the original 1-bit models, every parameter had to be either positive or negative. It had to have an opinion, essentially.
So it could be neutral.
Exactly. But by adding 0, you give the model the ability to perform what's called feature filtering.
Feature filtering.
Right. It allows the model to explicitly ignore certain inputs. It can look at a piece of noise or irrelevant data and just say, hey, multiply this by 0. It effectively turns that connection off. And that drastically improves the modeling capability compared to a pure binary system.
That makes total sense. It's like the difference between having to say yes or no to literally everything versus being able to say yes, no, or no comment.
Yes.
And that no comment is crucial for nuance.
That is a great way to put it. If you force a model to always react, you introduce noise. The 0 allows for sparsity. It lets the model focus only on what actually matters.
And despite this really radical change in how the weights actually work, the researchers point out that BitNet b1.58 still uses standard LLaMA-alike components. It uses things like RMS norm and SWIGLU.
It does.
Which means what for the average developer?
Which means it is compatible. You can plug this architecture straight into existing open source software like Hugging Face without having to rewrite the entire ecosystem.
Oh, that's huge.
It's a radical engine change, but it still fits right into the same car chassis.
So it's revolutionary, but it plays nice with the tools we already have.
Exactly.
Now, let's get to the real aha moment of the paper, the math itself. Because you mentioned earlier that multiplying floating points is the heavy lifting. How does this new model change that?
This is the part that gets hardware engineers incredibly excited. When your weights are strictly -1, 0, or 1, you don't actually need to perform multiplication in the traditional sense anymore.
Walk me through that, because my computer usually has to work pretty hard to multiply things.
Think about it. If you multiply any number by 1, it stays the same. You just add it. If you multiply by -1, you just change the sign to negative, you subtract it.
Yeah.
And if you multiply by 0, it just becomes 0. You do nothing.
So, wait. The complex matrix multiplication turns into simple integer addition and subtraction.
Exactly. Add, don't multiply.
Add, don't multiply.
That is the revolution here. You are swapping out the most expensive operation in computing, floating point multiplication, for the absolute cheapest one, which is integer addition.
That feels like cheating. Like, in a good way, but still.
Yeah. It feels like a cheat code for sure, and the energy implications are just staggering. The source cites a statistic that on 7-nanometer chips, this method reduces the arithmetic operation's energy consumption for matrix multiplication by 71.4 times compared to the FP16 baseline.
Wait, 71.4 times?
Over 70 times reduction in energy.
That is absurd. We are talking about reducing the energy bill of the most expensive part of the computation by almost 2 orders of magnitude.
Yes. And it solves the power limit problem.
What's that?
In chip design, you often can't make a chip faster simply because it would get too hot or draw too much power. It would literally melt itself.
Oh, wow.
But by switching to addition, you remove that thermal ceiling entirely.
Okay, but here comes the skepticism. Because I can make a car that gets 1,000 miles to the gallon if I give it a lawnmower engine, and it only goes 5 miles an hour.
Right.
It's extremely efficient, but is it smart? Like, does BitNet b1.58 actually perform well?
And that is the big question. Is it a Pareto improvement? Meaning, is it better without making something else worse?
Got it.
So the researchers compared BitNet b1.58 against a reproduced FP16 LLaMA model. Both were trained on the exact same dataset, the red pajama dataset, for 100 billion tokens.
So a true apples-to-apples comparison.
Completely fair fight. And the results show a very clear threshold. Starting at a 3 billion parameter model size, BitNet b1.58 matches the full precision LLaMA in both perplexity.
Which is how confused a model is, right?
Yes, exactly. Lower perplexity is better, it matches in perplexity, and it matches in end task performance. Zero-shot accuracy on tasks like ARC Easy, HelloSwag, things like that.
So at 3 billion parameters, the trade-off just disappears.
Completely disappears. In fact, the BitNet 3.9 billion parameter model actually outperforms the LLaMA 3 billion model.
Really?
And it does so while being significantly faster and lighter.
Let's talk about those speed stats, because faster can mean a lot of different things depending on who you ask.
Well, let's look at latency first. The BitNet 70B model, so a very large model, is 4.1 times faster than the LLaMA baseline.
4.1 times faster. I mean, that's the difference between waiting for a paragraph to slowly generate word by word and having it just appear instantly.
Exactly. And then for throughput, which is how many requests the system can handle at once on A100 GPUs, it supports 11 times the batch size.
11 times.
And 8.9 times higher throughput overall.
Wow. So if I'm running a server, I can serve almost 9 times as many users using the exact same hardware.
And with a significantly smaller GPU memory footprint. Because the weights are so small, you just don't need massive banks of VRAM to load the model anymore.
Which brings us to the future. The paper claims this defines a new scaling law. What does that actually mean for the AI industry?
Well, currently, we generally think larger model equals better performance, but much higher cost. This paper suggests a new equivalency entirely.
Oh.
They found that a 13 billion parameter BitNet is more efficient than a 3 billion FP16 model. And a 70 billion BitNet is more efficient than a 13 billion FP16 model.
Wait, let me wrap my head around that. You're saying I can run a massive, incredibly smart 70 billion parameter model, and it will cost me less energy and less time than running a relatively dumb 13 billion parameter model using the old tech.
Yes. That is exactly what the data suggests. It completely decouples intelligence from cost.
That sounds like it fundamentally changes where we can run these things. If it's that efficient, do we even still need a massive data center?
And that's the edge implication. Because BitNet relies on addition rather than float multiplication, it is incredibly CPU friendly.
Right, because CPUs are great at basic adding, but GPUs were always the kings of complex multiplying.
Exactly. This means high-performance models could realistically run efficiently on edge devices.
Like my phone.
Your phone, your laptop, maybe even smart home devices, all without needing a massive GPU cluster in the cloud somewhere.
So we're talking ChatGPT-level intelligence running completely locally on my phone without draining the battery in 10 minutes.
Potentially, yes. And there's another really cool benefit for the user, long sequences. You know how sometimes AI kind of forgets what you said 10 minutes ago in a chat?
The dreaded context window limit. Yeah, I already told you my name.
Right, exactly. Well, BitNet reduces the memory needed for what we call KV caches. Because the activations are reduced down to 8-bit, the model can remember or process twice the amount of text with the exact same resources.
That is incredible. So it's faster, it's cheaper, it can run on my phone, and it has a better memory.
And it enables things like one-bit mixture of experts or MOE. We don't need to get too technical here, but MOE models are usually huge and very hard to deploy.
Right.
But this compression could allow massive, complex MOE models to sit right on a single chip, which avoids all that slow communication between different chips.
All right, this all sounds fantastic, but surely there's a catch.
There's always a catch.
If this is so great, why aren't we using it today? Why didn't GPT-4 launch with this architecture?
The catch right now is the hardware itself. We are effectively trying to run software from the future on hardware from the past.
Because all our current GPUs, like the big NVIDIAs of the world, they're fully optimized for those heavy floating points.
Correct. They are built from the ground up to be really, really good at that complex multiplication we discussed. Now, they can do the integer addition that BitNet needs, sure, but they aren't designed for it.
Right.
They still have all that baked-in overhead for floating point math that we just aren't using anymore.
So we're basically driving that ultra-efficient lawnmower engine I mentioned earlier, but we shoved it inside a heavy Ferrari chassis.
Yes. It works, but it's massive overkill.
Got it. So what's the solution?
Well, the paper explicitly calls for new hardware designed specifically for one-bit LLMs. They actually mention Grok as an example of a company moving in this specific direction.
Grok, right, building language processing units, or LPUs.
Exactly. LPUs instead of GPUs.
So once the hardware actually catches up to this addition-only paradigm we're talking about, these efficiency gains like that 70x energy savings, that could actually be the floor, not the ceiling.
Exactly. When the hardware is specially fabricated for ternary weights, the efficiency could get even wilder than what we're seeing in this paper.
Incredible. So what does this all mean for you listening? Let's zoom out a bit.
We're really witnessing a fundamental shift. We are moving from a brute force era of AI where we just threw massive floating point numbers and massive amounts of energy at the problem to a much more elegant era of efficiency.
Ternary weights and integer addition.
It's a return to first principles, in a way.
It really feels like AI is finally growing up. It's stopping the binge eating of server energy and learning how to actually diet.
And that diet is exactly what makes it portable.
And that's the key takeaway for me. If this technology delivers on its promise, really powerful AI stops being something that lives exclusively in a massive server farm in the desert.
It comes home.
It comes home. It lives right on your device. It's private, it's blazing fast, and it's yours.
It changes the user relationship completely.
It really does. I'm going to leave you with a thought to mull over today. If we can truly reduce the energy cost of intelligence by over 70 times and run it locally on a phone battery, does AI cease to be a service we rent from big tech for $20 a month?
That's the real question.
If the cost of generation drops to near zero and it runs natively on your own hardware, does intelligence simply become a utility you own, just like the calculator app on your phone?
That is the multi-billion-dollar question right there.
Well, thanks for joining us on this deep dive. It's a 1.58-bit world, and we're just living in it.
See you next time.